Good afternoon, everyone. Thanks very much for joining in this technical webinar series. So the subject of today is evaluating the energy balance and efficiency of a whole hydrogen energy system. So just some housekeeping just before we get started. So this webinar is being recorded. The recording will be made available after the event, and that will be on the EI YouTube page. All participants will be muted except for the presenters. Please post questions using the Q&A function only, so please don't post your questions in the chat. And please remember as well to introduce yourself and what company or organisation or institute you might be from. So yeah, we have 177 registered for today's webinar, so maybe more will join or watch it after it's recorded. So my name is Tony Needham. I'm Technical Manager at the Energy Institute, and I manage our hydrogen programme, and I also cover electrical safety as well, so our electrical safety committee. Professor Ian Arbin will be covering the research report, which is titled Application of the Life Cycle Assessment Methodology of the Understanding of the Energy Balance and Efficiency of Hydrogen Value Chain Blocks. And Ian was the chair of the working group that delivered on that piece of research. And the research report itself was actually published in May 2022. Who's the Energy Institute? So we are a chartered professional membership body for people who work across the energy world. We're a registered charity. We have got 20,000 individual members and 120 company members, and we've over 40 technical partners supporting the work that we do. And we also have 100 technical committees and sub-working groups within our technical programme. We were formed back in 2003, and we were a merger between the Institute of Energy and the Institute of Petroleum, and we've been around for 100 years. So as part of the EI's 2030 strategy, the EI's role is threefold. It is to attract, developing, and equipping the diverse future energy workforce, informing energy decision-making through convening expertise and advice, and enabling industry and consumers to make energy lower carbon, safer, and more efficient. And we deliver this through a number of means. So we offer a variety of training courses. These are short and long courses, from a day long to a couple of days long and even longer. We do various outreach programs as well to engage future leaders. We host conferences, including International Energy Week, which is held in February every year. We host technical committees and engage global stakeholders. We host webinars and also host technical workshops. And we collaborate with a variety of industry bodies, including other institutes, associations, and regulatory bodies. We produce research reports and good practice guidance, and we continue to build on our transition topics. So this footprint really just outlines our main priorities. So overall, our priority is to build on health, safety, asset integrity, digitalization, climate resilience, and energy. And our focus is on the four main pillars. So that is looking at decarbonising fossil fuels. So that includes CCUS, hydrogen and methane management, deploying sustainable fuels, such as aviation biofuels, integrating power systems, renewables, and better managing energy efficiency. So the EI has launched an academy which offers expert-led training courses and free learning resources across a wide range of topics for all levels of capability and experience. The EI Academy can support your professional development journey by helping you to upskill or reskill for the energy future. So if you do want to know more about the Energy Academy, please visit the website, which is just visible there on the screen. The EI has a growing portfolio of training courses in hydrogen. Two notable courses to mention are hydrogen-based energy systems courses. Both are self-paced online courses that you can complete in your own time, wherever you are based in the world. So one you can see there is a 5-hour course and the other is 10-hour. And again, you can go to the training website to get some more information on the hydrogen training. One final program to mention is our Executive Leadership and Energy program. This is a 10-day program designed to develop strong future leaders who will be instrumental to the success of the energy transition. And again, there is a website available if you wish to find out more information on that. Just going on to the Technical and Innovation program, which is the department that I work in. So the aim of the Technical and Innovation Programme is to accelerate the transition through collaboration in diverse energy sectors with a more recent proactive shift towards low carbon, so hence the hydrogen and CCUS. The Technical and Innovation Programme is a hub of excellence for industry. We have technical experts from over 50 leading energy companies, regulators, academia, and we all work together to pursue shared goals and outcomes. We cover all energy sectors, so oil and gas, upstream, midstream and downstream, onshore and offshore, wind, thermal power, solar, battery storage, power systems, hydrogen and CCUS. EI's Good Practice and Innovation Programme is instrumental in keeping people, assets and the environment safe and secure. And we have over 750 titles published. So this is just the technical committee organogram. So the Scientific and Technical Advisory Committee is the epicenter of the technical programme. And supporting that programme, we've in the region of about 50 technical partners involved, and they approve and fund annual programme of works. And the committees cover 3 main overarching themes, and that includes fuels and fuel handling, health, safety and environment, and transition. So just a few words on the Hydrogen Committee. That's the committee which I manage. So we had our first committee meeting back in 2019, and recently we've held our 12th committee meeting. The committee itself comprises of over 40 members, including energy companies, regulators, academia, and independent experts. And supporting the committee are a number of working groups as well, which are populated by technical experts to deliver on individual projects, such as the energy balance. We look to help identify and address the regulatory, safety, and technical challenges facing companies wishing to be involved in the hydrogen space. And the committee itself is chaired by Donald Smith. This is just a timeline of the development of the hydrogen programme itself. So initial discussions were held back in 2018, and in 2019 we had a number of stakeholder engagement workshops to work out, what topics we should be working on, what were the challenges and issues facing industry. And we identified 6 topics, of which one was the energy balance, and you can see there in red that was published, that was worked on and then published in May 2022. And currently we are working on, 2024 projects, and we're also scoping out and defining what our work programme will be for next year. So this organogram really just shows the main technical committees, but those in red are also interested in hydrogen. So it's not just the main hydrogen committee that covers the topic of hydrogen, but other committees such as the Power Systems Committee, the Environment Management Committee, the Corrosion Management Committee, Aviation Committee. All these committees have also got an interest in the hydrogen topic and do some work related to hydrogen. So this is just showing, the value chain and the areas which we work in. So those highlighted in green are the areas that we cover. So production, storage, transmission and distribution, and mobility. But those highlighted in red, we don't cover because another institute covers those areas. So we do cover quite a lot within our hydrogen programme. So this is really just to say that we have many publications already. The program is 4 years already in progress. So we have a number of publications already published, which are available on our website under hydrogen. And this is just a list of the different titles. So there's about 9 different titles there already published. And we are working on a whole range of current topics as well, which obviously will be published in the near future. And soon to be published as well. Within a matter of weeks, we have got 4 other titles as well. And the hydrogen compression, actually, Ian worked on as well. He delivered that piece of work. So we'll be hosting a webinar at some point on hydrogen compression. So over to yourself now, Ian, to cover the report evaluating the energy balance and efficiency of a whole hydrogen energy system from production to consumption.
Yeah, thanks very much, Tony, for the introduction. Yes, well, without further ado, we'll process the slides for this. So if you go to the next slide, please, Tony. Just wanted to give a bit of a personal background, so you know what the experience I have in speaking on this subject. I'm an unusual combination of a career businessman, chartered engineer, chartered environmentalist, and part-time academic. So I address this topic from much more than the viewpoint of a single vested interest. Spent over 50 years in manufacturing industry, mostly in the UK, but also in other countries. Started out as an apprentice, worked through various roles before moving into senior corporate management and running several companies in the sector. For most of those 50 years, I've been involved in supplying gas compression equipment to the Energy Institute around the globe, and particularly in hydrogen service. So I know the sector very well. And for the past 28 years in engineered solutions consultancy, I've been heavily involved in sustainable engineered systems, in particular their impact on the global climate and ecosystems. So you can see I'm taking a very, very broad view of this topic. Next slide, please. The abstract for the webinar you've already seen, I would assume, because it was on the registration page. So I won't go through that again, and we'll go into the main presentation. Next slide, please. So as part of the Energy Institute's hydrogen program that Tony's just been talking about, the HY 2002 working group was set up to deliver a report on evaluating the energy balance and efficiency of a whole hydrogen energy system from production to consumption. And the goal was to understand the efficiencies and inefficiencies of the whole hydrogen energy system and quantify the energy intensity and resultant greenhouse gas emissions compared to other fuels and energy vectors, to produce an independent, holistic view of all options from production through transmission to utilization. And observing in the course of this that many studies that I've seen in the hydrogen field recognize only localized data, every effort has been made in this study to do something a bit more useful and to utilize whole life cycle analysis. So we're looking well beyond the immediate impacts of whatever we're doing in the hydrogen sector and looking at the whole life cycle, which I think makes this report rather stand out from many others. Next, please. So competing solutions were assessed for the whole hydrogen value chain in 3 discrete fields of application. First, production of green hydrogen and blue hydrogen, with grey hydrogen used as a benchmark. Second, transmission, storage, and distribution, and thirdly, consumption or end user requirements. I think this is quite important because there's a lot written in the literature already about production of hydrogen and consumption of hydrogen. We found there's very little in the section in the middle, transmission, storage, distribution. And there are some major assumptions that have been made in many reports that this bit is going to be fairly straightforward and easy compared with the other two. Well, our report I'm presenting today finds rather differently, as you'll see in a few moments. So the study has a present-day UK context. You can't cover everything, but it's UK-based, it's present-day. That is to say, it does not take credit for advances in technology or possible improvements in efficiency, which may or may not be actually realized. I've been around this business long enough to know that good ideas don't always come to fruition. And so we've tried to take a pragmatic approach of looking at the present day context. Next, please. So as with all Energy Institute publications, great care has been taken to accurately present the salient facts emerging from the research, enabling correct decision-making to be based on the presented facts. For instance, it does not presume that hydrogen is the correct answer to the question, but it presents data to enable readers to make their own informed decision. Now, I'm not saying that hydrogen isn't the answer. I'm saying that is not the presumption in the report. I was amazed in the research we did for this, just how many reports seem to be written to lead you to a predetermined answer, which to me, as an engineer, is not the right way to do it. And I just wanted to add that there was no pressure from any quarter to influence the data presented in the report, or in any way to support other predetermined decisions which were made without the relevant facts having been available and taken into full consideration. I think this is important because I would, when I say there was no pressure, actually there was some pressure, but we didn't take any notice of it because we wanted a completely independent and factual report be produced. Next, please. So this is what the report looks like. You've already seen it in Tony's presentation. Application of life cycle assessment methodology to the understanding of the energy balance and efficiency of hydrogen value chain building blocks. The title is a bit different from the original brief that was given to the group that I've already described. I think if I'd chosen the title, I'd probably preferred a rather shorter one, but it does accurately describe what we did. But I just hope that people haven't found the title too off-putting. Certainly recommend that you, if you haven't already, you get a copy of it and read it. The report was commissioned from Genesis Consulting, so it was an independent report, and it was published, as Tony said, in May 2022. Next, please. And I just wanted to give a current update, because obviously this report was done and published well before COP28 last year. I was struck at one of the outcomes or pledges that was made at COP28 in Dubai on energy efficiency, which is until recently has been a largely overlooked part of the energy transition, and indeed of UK energy policy over many, many years. It's occasionally been mentioned, but very little has been done about it. And this has led, I think, to some experts, even practitioners, believing that it is a less important measure than the others that we are looking at in the energy transition. But the largely unexpected wording of the pledge signed by the UK and many other countries in Dubai in December last year, that we must double the global average annual rate of energy efficiency improvements from around 2% to over 4% every year until 2030, has hugely raised the significance of energy efficiency to an unprecedented level, and has made this HY 2002 report of even more relevance to the hydrogen value chain, because it is mostly about efficiencies. So could have the next slide, please. This was the methodology that we used in the report. I don't want to spend a lot of time on this, but it's so on the x-axis of the graph, if you like, we are we're assessing end-to-end efficiencies and emissions profile for the full value chain, and on the y-axis we are assessing competing solutions within technology blocks, and we split this into the three sections I've mentioned, which, looking along the top of the table, hydrogen production first, and then transmission, and then consumption. And then within each of those sections, we, for instance, in production, we looked at green, blue, and grey hydrogen, and we looked at the processes you use in that, alkaline PEMs for green hydrogen, autothermal reforming, steam methane reforming for blue hydrogen and grey hydrogen. And we looked at each of those scenarios and made analyses and comparisons. And moving to transmission, we looked at compression from very high pressure to medium pressure to low pressure, storage in pressurized tanks, pipelines, cryogenic storage, geological storage, and the different requirements and attributes of each of those. And we looked at distribution by means of shipping, by trucking, by railways, through existing pipelines and through new pipelines. And on consumption, we looked at electricity generation, combined cycle gas turbines, combustion turbines and combustion, fuel cells, cogeneration, combined heat and power. On heating and cooling, we looked at domestic, we looked at high heat industries, low temperature industries, and in transport, we looked at railways, personal vehicles, ocean shipping. So you see, we did cover a very, very large scope, and there is a lot of analysis and reading in the report, come up with the various conclusions that we did. Okay, next, please. Right, this is an overall diagram looking at the efficiency range throughout the value chain. And you can see along the bottom of the diagram, we've put the feedstock, production, compression, distribution, storage, consumption. And you can see where the various inefficiencies are. That's quite helpful to understanding the whole value chain. And you can see the major areas of inefficiency in the hydrogen value chain are production and consumption, not so much in distribution. And if you look at the production part on the left, upper left part of the diagram, you can see on blue hydrogen through autothermal reforming as the higher line, and green hydrogen through electrolysis as the lower line of the blue phase, and you can see that they are both quite inefficient processes, which I think a lot of people don't take into consideration. It goes back to what I said before about we haven't taken efficiency very seriously in this country in the past, energy efficiency, and now I think we have to. And so we have to be very honest and pragmatic about what we're assessing here. Blue hydrogen production is certainly quite a bit more efficient than green hydrogen production, but this will all help us in our decision-making processes. Moving to compression, you can see efficiencies are quite high, and also through distribution is relatively high, particularly if you're looking at a new pipeline, less so if you're looking at repurposing an existing pipeline. And then in consumption, just this graph just looks at two consumption areas. In a fuel cell, you get some inefficiencies, in considerable inefficiencies in consumption. But compared with a simple cycle gas turbine, it's very, very good. The simple cycle gas turbine, as I think we all know by now, is a pretty inefficient way of doing anything. So distribution and storage have only minor impact on overall efficiency losses and emissions for the distances associated with a regional network, which we've taken as about 500 kilometers or more, and are almost negligible for local transmission, less than 100 kilometers. However, there are huge practical challenges, and I want to move on to some of those. Next, please. Right, if we look at the value chain for blue hydrogen versus natural gas, you I don't want to spend too much time on this because it is just a graph which should explain it quite simply. The red line is the blue hydrogen value chain, and the blue line is natural gas value chain. Again, I didn't pick the colors, or I might have picked blue for blue hydrogen, but just bear in mind it's red. And you can see that compared with natural gas, there is quite a lot more energy flow requirement in kilowatt hours on the y-axis there, before we get to the storage, transmission, consumption, and delivered. So the interesting thing to note there, though, is in the little box at the right-hand side of the diagram, which shows the emissions intensity in grams of CO2 equivalent per kilowatt hour of natural gas at 304, compared with blue hydrogen from the UK continental shelf at 61, and blue hydrogen from LNG at 98. And although both of the blue hydrogen figures are much better than natural gas, it does highlight the point that LNG feedstock, when you do a whole life cycle analysis, increases blue hydrogen emissions by 60%, which is pretty colossal. And when you think that our natural gas from the UK continental shelf is in decline, and that in the future more and more of our natural gas will be supplied in the form of LNG, then you can see we are going in the wrong direction here in terms of efficiencies. And surprisingly, this is not something I've read anywhere in all the reports that have done on where we will get our natural gas from in the future. And it's natural gas, whether we use it directly as natural gas or as converted indeed to blue hydrogen, this really needs to be taken into consideration. Next slide, please. So the next slide, these are just two sample slides we've taken from the report. They're not changed in any way. They're the same slides. So this is comparing electricity from the grid in red and electricity from in a fuel cell green fuel cell application, green hydrogen fuel cell application. And again, you can see that there are quite significant inefficiencies in production and in the consumption of green hydrogen compared with using electricity from the grid. Now, I'm sure many people would say, well, that's obvious because you can't make something from grid electricity and have a resultant product that is more efficient. It has to be less efficient. But again, I see very little reference to this in any of the literature or any other reports that we've read. And it does show quite graphically that if grid power were used to produce hydrogen by electrolysis, then emissions are as much as 180% greater than using power directly from the grid. Now, this is not necessarily a showstopper, but it is something that we must take into consideration. And I'm just not seeing that generally in the industry at the moment. But of course, by using green hydrogen, emissions are reduced by 85% compared to the electrical grid, but almost 3 times as much power generation is required. Is that important? Well, perhaps it is, because there is a view in the world today that wind energy, for example, that you would use for the electrolyzer is the cheapest form of power, and the reason for that view is that because wind is free, you don't have a fuel cost in association with the power generated from it. But it does mean that you need very much more capacity to produce the same amount of energy flow, and all of that has to the capital expenditure of all that new equipment is very, very large indeed. So it's not entirely true that that wind energy is very cheap. It appears so, and believe me, I've got nothing against wind energy. I've worked in the wind sector for decades, but we just have to be realistic and recognize that there are inefficiencies in that area which have to be taken into consideration in any analysis we do. And our experience is that is rarely done at the moment in the UK. Could I have the next slide, please? So from preceding graphs, we can see that the major efficiency losses are in the production and consumption fields, whereas efficiency in transmission are comparatively very low. However, these are measured as a proportion of the very high flow rates of gas in a pipeline and tend to conceal the fact that the gas pipeline losses and booster compressor drive power requirements are very much higher for 100% hydrogen than for the original natural gas for which they were designed. And this is shown clearly in the two following tables, which is where we start on the energy balance part of the report, really. Next, please. So you can see here, this is one of the tables lifted directly from the report without any change. And it considers transmission pipeline pressure drop per kilometer for 100% natural gas, 20% hydrogen blend, and 100% hydrogen. And you can see that in the three main columns, we've in each case looked at operating pressures of between 70 bar gauge and 40 bar gauge, which is what you would normally expect in a typical pipeline, 70 being from the booster station, 40 what it falls to before it hits the next booster station. And the flow rate in millions of standard cubic feet per day, which was just the figure that the industry uses, so we used it. And you can see our natural gas for a flow of 1,500 million standard cubic feet per day on 20% hydrogen blend, to get the same energy value in the gas, you would require 1,743 million scuffs per day. And when you move to 100% hydrogen, that rises to 4,877 million standard cubic feet per day. So, and that is just to pass the same energy flow through the pipeline. So as a result of this, and then in addition to that, you've got to look at the delta P per kilometer, which is what this diagram is showing. And you can see for in bars per kilometer, you can see that the pressure drops are considerably greater with hydrogen than they are with natural gas. And the final bit there is the bottom, the factor to use is just how you have to up rate all of these all of this equipment for the different conditions. So said most of the bit in the bottom. Velocity restrictions not being considered. Further restrictions would increase the derating factor for hydrogen, but in practice, if this was significant, it is likely that this would result in the requirement for the installation of new piping. All right, next, please. So the next table, table 5.6, again lifted straight from the report, shows the transmission pipeline power requirements for existing pipelines. Again, there are other graphs that look at the same figures for using new pipelines, but this is particularly for using existing pipelines, because there is a lot of interest at the moment in repurposing hydrogen, natural gas pipelines. And you can see there that in the first column on the left, the booster power for the same energy flow in the second column would require for that duty, that 1,500 million standard cubic feet per day would require a drive power for the compressor of 39 megawatts, which is a big compressor. You add just 20% hydrogen blend to that gas flow, and you would immediately have on the same conditions, have a drive power of 48 megawatts. And if you go to 100% hydrogen through the pipeline, which is understandably the objective, then you get a colossal 170 megawatt to do the same duty. And as you can see, that's all based on the same energy flow. And then because the pressure drops in the third column over, you can see the number of booster stations you would need over this 500 kilometer length moves from 3 with natural gas to 3.5 with 20% to 4.4 with 100% hydrogen, which would lead you to a total power, if you add all of those together, in the next column of 117 megawatts rising to 169 megawatts to 745 megawatts for the 100% hydrogen condition. Now, I don't read that in any of the reports that I've seen. And indeed, I have read reports which say that it's expected that the compression requirement moving to 100% hydrogen will not be very considerable or will be minor. That doesn't look minor to me. And I would just say that in the second body of work that I've been involved with for the Energy Institute on hydrogen compression, part of that was to verify these numbers because they are astonishing. And we did that as part of the report. And although they are, we did it by comparison with quotations we received from compressor OEMs, so they would be pretty accurate. And we found that while all of the numbers there are a little high, they're not very high. Yeah. So they're within the normal margin of error that you would expect. So although Genesis calculated these numbers in-house, we were able to show in the second body of work that that they're reasonably accurate. So I'm quite satisfied with that. Next slide, please. So the main reason for the very much higher flow rate required for hydrogen compressor, again, I underlined, to deliver the same energy flow, is that the volumetric energy of hydrogen, 10.4 megajoules per cubic meter at standard temperature and pressure, compared with natural gas, which is 38 megajoules per cubic meter STP. This is a straight ratio of 3.65, and most of the factor of 4.6 used in the preceding tables can be explained by this. Now, this is not a factor that can be considerably reduced by more research and development. It is subject to and is simply the laws of physics. And proposals, for example, to repurpose natural gas pipelines for ultimate use with 100% hydrogen must take these laws into consideration. That's I think if you take nothing else away from this presentation, please take that away. We need to make sure that we're in all of what we're doing for the hydrogen economy, that we are always making true and valid comparisons and not just assumptions. Next, please. Right. Well, this is just referencing what I've talked about already, and Tony has mentioned that the HY 2306 report is verify and build on the findings and outcomes of the HY 2002 report, and to investigate the worldwide availability of a broad range of gas compressors for hydrogen service across the hydrogen value chain. And this report on hydrogen compressor was completed a couple of months ago, and it's currently with EI for final editing. And we're expecting it to be published, well, probably not during spring now, but very early summer, I would think. Next, please. Right, so the key conclusions of HY 2002 on energy balance and emissions. Both blue and green hydrogen require more feedstock to deliver the same energy value as natural gas or direct use electricity, respectively, due to the efficiency losses of hydrogen production, as we saw in the graphs I showed you. Hydrogen can reduce overall greenhouse gas emissions considerably compared with current energy vectors such as natural gas and electrical grid production. Next. Future uses of hydrogen. Blue hydrogen appears suited to use in industrial clusters where there are few ready alternatives to the use of natural gas. Green hydrogen cannot currently be produced in high capacities. However, its high purity and relative flexibility in production locations mean it could be suited to smaller integrated developments. And green hydrogen captures renewable energy as a dispatchable vector similar to batteries. However, this process involves significant increases from the original energy produced. Next, please. So back to hydrogen transmission, the most significant issue to overcome for long-distance pipeline networks operating at pressures up to 90 bar in the UK is that the compressor facilities may be an order of magnitude larger and more expensive than equivalent natural gas facilities. There are significant drivers for having hydrogen production facilities close to major consumers without the need for booster stations. So we will have to, I think that there's no getting away from the fact that this will be very expensive to do. And it will require input at government level to fund this, in my view, because it's not easy to get a return on the investment otherwise. And this just needs to be taken into consideration. It could easily be an order of magnitude larger and more expensive. Transporting hydrogen by truck in pressurized containment is quite inefficient over long distances, but over short distances, the losses are modest, less than 5% for a 100-kilometer round trip, including compression, to 250 bar. And the next one, please. Hydrogen storage, there's been a lot of talk about this, and we did cover this in the report, although I haven't really mentioned it in this overview. But just to note that hydrogen compression for storage will be subject to similar physical constraints as those for pipeline transmission. We're again talking about very large machines. And regardless of the type of storage, gas has to be moved from its production source to the storage location and then further compressed to much higher pressures, up to 250, 350 bar for storage. It then has to be transmitted to its final point, which may also of use, which may also require compression stroke expansion facilities. And the type and size of compressors used for hydrogen storage will be even more complex than those used for transmission due to the very much larger pressure ratios and differential pressures involved. So both the CapEx and OpEx costs, that's capital expenditure, operating expenditure, as well as physical footprint, will be considerably higher. And when I say considerably higher, I mean considerably higher than the compressors used for transmission. Next, please. So the economic consequences, the emission savings from hydrogen usage would come at considerable economic cost, considering both the capital expenditure on new equipment and the increased consumption of feedstock, gas or oil, electricity on operating costs. This is particularly true for gas pipeline booster compressor stations, where with equipment which would have to be totally replaced and or renewed, and where driver power, physical footprint and capital expenditure could well be an order of magnitude higher than that of current practice. Next slide, please. I thought so. That's the end. So many thanks for your attention, and I look forward to any questions you might have.
Thanks very much for that, Ian. That was very informative. Are there any questions on the Q&A? No, I don't see.
Tony, we do have a question in the chat actually from, I believe his name's Miguel, which is, what is the reason for the difference in the compression of blue hydrogen and green hydrogen?
Sorry, I could you just repeat that? I didn't quite understand the question.
Yeah, sure. So it's, what is the reason for the difference in the compression of blue hydrogen and green hydrogen?
Okay. There isn't any difference between the compression of blue hydrogen and green hydrogen. One of the, in fact, it's a good question, because it enables me to point out something that I haven't done so far in the presentation, which is hydrogen is colorblind. So whether you use blue hydrogen or green hydrogen or gray hydrogen or brown hydrogen or any other color of hydrogen, it's the same gas chemically and physically, and the compression equipment will be identical. So it's not moving from green hydrogen to blue hydrogen or the other way around that makes the change in the compression. It's moving from natural gas to hydrogen, and the simple equation you use there is, natural gas has a molar mass of around 18. Hydrogen has a molar mass of around 2. And it's very much easier to compress and less power hungry to compress natural gas than it is to compress hydrogen. So that's the only difference. The big differences between hydrogen, blue hydrogen and green hydrogen are in the production process, not in the compression process. But thanks for the question. That's helpful.
We have a question in the chat and one in the Q&A as well. Maybe we'll go to Q&A first, if you want to read that out, Tony.
Okay, yeah, so this is from Matthew. Apart from the environmental friendly advantage derivable from the types of hydrogen fuel, is there any significant difference in their heat value?
No. No, there is no, as I just explained in the last answer, that there is no difference in chemical properties between the different colors of hydrogen. They're just to tell us how it was produced. And as you say, there are significant environmental advantages of one compared to the other. But once it's produced, it is just hydrogen, and the system cannot tell the difference between blue, green, grey, brown hydrogen.
Okay, so there's some questions going into the chat. Let me see. Okay. Okay. Are there any technological advancements or process innovations identified in the study that could enhance the efficiency of green hydrogen production and utilization in applications such as FCVs or CHP?
Yeah, well, that is a bit difficult to untangle that question, because I think it starts out by talking about production and ends up in consumption, which are different areas. So on production, yeah, I'm sure that in time, electrolyzer technology will get better. And be more efficient. But going back to one of the original comments I made, that might happen, it might not happen. And there's nothing I know of on the at the moment that says that technological advancement will bring major improvements to the efficiency of green hydrogen production. In terms of the usage, you know, there are many different types of consumption usage of hydrogen with many different processes and technologies, and I'm sure there will be in many of those there will be some efficiency improvements. But we've got a huge mountain to climb in terms of efficiency improvement, and it's not a given. So as things stand at the moment, the very great likelihood is that, yes, all of these things that we've discussed are technically possible, but, you know, how do we afford them is going to be the question.
Okay, there's another one. It's from Andrew Cockburn. Has any account been made for the reduced lifetime of existing pipelines if they are repurposed for hydrogen due to the hydrogen embrittlement?
Yeah, thanks for that question. There's a huge amount of work being done at the moment on the whole hydrogen embrittlement issue, and that I think is recognized in many of the reports that have been written on the subject. And I think by and large the UK pipeline network looks as if it will be suitable for 100% hydrogen up to certain pressures. That, I admit, is covered in most reports. What is not covered is the compression requirements, and I've seen that missing in many reports.
Okay, another one. Since consumption efficiency of hydrogen in gas turbines is currently low, around 30% from the slides, what can be done to improve the efficiency of converting hydrogen to energy in power plants? Do we need to invent new gas turbines to use hydrogen?
Yeah, interesting question. The problem is gas turbine technology as such, is already very well advanced. There have been colossal improvements in gas turbine technology over the past 50 years, with some of the world's largest companies like GE and Siemens involved in that. There isn't now much room for improvement, but hydrogen acts in a very different way from natural gas, and if you want to, I mean, yes, you could redesign. You have to, in many respects, redesign a gas turbine specifically for hydrogen, but you won't get away from the very low efficiencies of open cycle gas turbines. So the answer, part to answer, is to not use open cycle gas turbines, but to use closed cycle gas turbines, which will, as they do with natural gas, will greatly improve the overall efficiency, although not to very high levels. You still get a lot of energy wastage, mostly in the form of heat. But it's certainly an improvement over an open cycle gas turbine, to use a steam turbine bottoming cycle. But the big thing we miss in this, and it's well beyond this report, but in general, is that in the UK we have a history of wasting most of the heat from the cycle, which is, you could get a combined cycle gas turbine with about 55-60% efficiency perhaps, but the rest of it goes as heat. So the real question is, if you want to improve the efficiency of the cycle, why don't you find a way to use the heat? That's what other countries do, but we tend to just like to waste it to atmosphere and water courses. So there's a challenge.
Okay, so there's 2 more questions in the Q&A section. So would the inclusion from other renewable sources, although it's inefficient, mitigate the power-hungry hydrogen production phase?
I suppose you mean, instead of wind, using solar or hydro or whatever. Well, yes, they all have somewhat different levels of efficiency, but they're all, and I think this goes back to the point I raised right at the beginning about how are we going to accommodate this new requirement from COP28 that we have to improve energy efficiency throughout, while most forms of renewable energy are relatively inefficient. And lest I come over as somewhat anti-renewable in saying that, let me assure you that I'm actually in my this year marks my 50th year in that's 50 year in renewable energy, which is we didn't even know it was called renewable energy in those days, but it was still a very good thing to do. So I'm a huge fan of renewable energy, but I recognize that the one thing most renewable energy sources are not, is very efficient. So I think there's a major challenge there for the UK, for the world, really. It's dead easy for the IPCC and the organizers of COP28 to simply slip in, we have to improve energy efficiency. But the fact is, that's going to require a major effort across the world as to how we actually do that, given the trajectory we're on at the moment.
Yeah, I think you've touched on the next question. What are the latest developments in industries to improve the efficiency in the production and transmission? For instance, is there any particular technology employed in the CCUS during production of hydrogen?
Well, interesting question. I think, as I said during the presentation, there's a distinct limit to how much efficiency improvement you can make in the technology. You know, the technology is already very advanced. We've made huge improvements on it over the years. But everything we do tends to make things, the whole systems, less efficient. And you raised the very interesting point about CCUS, which, you know, is inescapable if we're going to use blue hydrogen. We have to use CCUS because there's not really any other way of doing it. But CCUS is in itself a technology that makes the whole system considerably less efficient, not more efficient, because there are huge energy costs involved with the transmission and storage of CO2. I've done a lot of work over the years in CO2 compression, and it's very, very power hungry. It's a heavy gas, 44 molar mass, and requires a lot of power that you wouldn't otherwise have needed to use. So, you know, there is a very interesting challenge in all of this, that how we make things more efficient while applying things that are less efficient. There's a conundrum there.
Okay, another question. How do other transport vectors, such as conversion to ammonia, compare in efficiency to pipeline transport?
Okay. Well, you can put ammonia through a pipeline. That's not that's not difficult to do. And if you look at, well, we'll start by looking at pipelines. Ammonia has a molar mass of around 17, 18. So it's very similar to natural gas. So you could actually put ammonia as a direct substitute for natural gas into a gas pipeline and have none of the problems that you would have associated with putting hydrogen in those same pipelines. So that's a big plus. The problem is that ammonia is quite an aggressive gas, and it's well known for its capability to eat yellow metals. So you have to look at the metallurgy throughout the system to make sure you don't have anything in there that's incompatible with ammonia. I know this very well from 50-odd years experience of ammonia compression. And the other thing about ammonia, of course, is it's an absolutely fantastic gas in the way it behaves, but it is pretty deadly. And so while leaking hydrogen might lead to conflagration, leaking ammonia could wipe out populations, and it's a particularly nasty way to die. But it sounds like I'm trying to put everybody off, but I'm just saying that this is its downside. Now, we've worked with ammonia for many, many years and know how to contain it, but that is its problem, and has to be taken into consideration. So when you look at shipping, then shipping ammonia is again easier. You can easily drive the ship's engines with using ammonia as a fuel. So transportation by ship is not a problem. Again, subject to the same dangers of ammonia, and very, very much cheaper than, say, going for liquid hydrogen, which is, gaseous hydrogen is going to be expensive. Liquid hydrogen will be much more expensive again, just because of the process required to get the temperatures down to 20 degrees above absolute zero. So ammonia, for instance, is a good option, but it has its drawbacks.
Okay, so another one. There's just I think there's two more questions. So in terms of cost, what role does policy levers and market challenges make in influencing the cost efficiency of producing blue and green hydrogen?
Very difficult to answer that question, because energy policy, such as it is in this country, doesn't really take that into consideration. What we have at the moment, and this is in comparison, say, with other more enlightened countries, or governments, more enlightened governments, and this isn't partly political, by the way. We've had the same sort of approach through every government in the past 30 years. So, and that is the government sets targets, whether or not they're realistic, and leaves it to industry, particularly the oil and gas companies, to meet those targets. So government actually it sets the targets, but it doesn't provide a means of achieving the targets, and it certainly doesn't provide the capital for building the equipment to reach those targets. That has to be done somehow by government, by industry. So I, in all honesty, I don't think that policy, such as it is in the UK, really takes real world finances into account at all. It just sets arbitrary targets. I don't know if that answers it or not.
Thanks very much, Ian, and thanks again for your very informative presentation and answering all those questions. So we're coming to an end now. We've just got 2 minutes left. So I just want to mention that there's another webinar next week, next Tuesday, and my colleague has put the web link to register for that. It's Tuesday next week. So you can click on that link, and that will bring you to where you need to go to register. Also, we'll be arranging a webinar on hydrogen compression in due course, a little bit later on in the year when the document is published. And also keep an eye out next year, because we'll probably be doing some other work, an extension of this work on energy balance on hydrogen derivatives. So that's likely to be a piece of work that we will develop next year. Yeah, as I say, keep an eye out for that. So thanks very much, everyone, for participating in the webinar, and hopefully you can join another one in the near future. Okay, thanks, everyone. Bye.
you.